I'm Natalia, and as it was said, I'm a lecturer at Bournemouth University. And today I will talk a little bit about the research that I do with Erlang. And this is done in cooperation with researchers and students from Glasgow University. And the reason for that is that until July 2017, I was a research fellow there. So I will be introducing students as we go through their project, but my main research collaborators at Glasgow University are Gerardo Aragon-Camarasa and Phil Trinde. So Gerardo, he's a lecturer and he specializes in visual robotics and distributed robotics. And Phil, probably many of you know him, he's a professor and he specializes in parallel programming and distributed systems. So today I will introduce you to three topics, three very small student projects. And the reason for that they're really small is that I'm just starting to do research and there is just not enough funding to do large-scale research, so these are just small bits that I do with the students. And these are comparing Erlang with other languages, and these are for servers. The second one is analyzing scalability of ROS, and the third one is a comparison of Erlang and ROS performance. And I will just introduce you details as we go. So the first one is comparing languages for engineering server software. And this project was done by our student, Ivan Valkov, with Phil. And motivation for that is that to program or to develop any system, we need the right tools. And language is one of those tools. And then the number of requests grows, and we just don't know which language is it better to choose very often. And for that, we need low communication latency, fast process creation, and massive number of processes. So we looked at quite a large number of programming languages, starting from C++ and C with pthreads, with OpenMP. Then we looked at Java, Erlang, Go, all sorts of languages. We looked at the different computation models, coordination models, then compilation. We also look at their popularity, because if the language is just really small and unpopular, there is just no point investigating anything in there. In the end, we decided to go with these three languages. So it's Erlang, Scala with Akka, and Go. And the reason for that is that actually Scala with Akka and Go, they were influenced by Erlang, and they have quite interesting characteristics. They're very favored in server implementation world, so we decided to compare how they perform. So you know quite a lot about Erlang, but just a reminder that it's a functional programming language. It has dynamic typing. Concurrency is supported by Akka model. And then when we talk about fault tolerance, it's about supervision and let it crash philosophy. Go is a little bit different language. It's a procedural language, and it has static typing. Concurrency is supported by communicating sequential processes. And here, to actually support this concurrency, we use Go routines and channels. And the third language is Scala with Akka. So it's functional programming language, but it's also object-oriented programming language. The typing is quite interesting because it has this static typing from Scala and dynamic from Akka. And then concurrency is again from Erlang influence, and it's Akka model. I'd like to warn you that the research that we'll look at here, it won't look at fault tolerance. This is a really, really important characteristics, and we all know that the performance changes as soon as we introduce fault tolerance there. But we decided to start up with something, and first removing fault tolerance and not considering it, that it will be a good start to explore the parameters of the languages. So the first benchmark, it was an Intel benchmark, NPI, and it's a really simple one. So we just took the one that it was, and we converted it to different languages. So the 3 that we used. And this is a really simple one. So we have 2 processes, and this just ping-pong messages. So send, send back, send again, send back, and just go round and round. So this experiment we ran on just a laptop, Windows 10, 2 cores, 300, 3 gigabytes of memory, and then we have a CPU of 2.6, no, that was something different, 8 gigabytes of RAM. And then the message size, we looked at different message sizes, but this figure is for 50 kilobyte messages. And so on the left, I'm sorry, on the y-axis we have time, right? So the lower the better. And then on the x-axis we have the number of repetitions. What we mean here is that message sent, send back, from A to B, we send message, send it back, and then we repeat this process over and over again. I'd like to point to you that the number of repetitions is a logarithmic scale. So it's important to know. And here we just compare 3 languages. And the result here is that Erlang and Go perform quite similarly, and Scala is a little bit behind. And then we did another benchmark, and this one analyzes the creation time. So sometimes we need a system when we create lots of processes, but it doesn't matter that all of them start, communicating with each other. Sometimes they're just dormant, they just stay there. So, and this one, we analyzed how long it actually takes to create all those processes. And we did 2 experiments. The first one, we just analyzed how many processes can a language handle, right? And the results were quite interesting because, so Go, it was the smallest one. It was around 3 million processes. Then it goes Erlang, around 9 million processes. And the largest one of German processes that a language can support is around 11 million, and this is Scala with Akka. Then we thought, well, sometimes we don't want to create the maximum number. Sometimes we want to create a fixed number of processes, but we want them to be created really quickly. And this is the second figure. So we have time, we have number of processes, and here we created up to 100,000 processes. And the picture here is a little bit different. So Erlang and Go perform almost similarly, and for Scala it takes longer. So the lower, the better here. And the third benchmark, it was on concurrent process throughput. So what we did, we created 2 processes. One of them, like main process, is a supervisor process, and another one that process collects information on how the system creates. And the supervisor process, it just creates those pairs of worker processes. They just communicate with each other. And here we created up to 120 pairs. And again, we compared different languages, but this time we used a little bit different hardware. So instead of just a laptop, we used our server at Glasgow University, and it was a Scientific Linux, 16 cores, and 64 gigabytes of RAM. And so here, the higher, the better. The higher throughput is, the better. And this is messages per minute. And then on the axis, we have the number of those pairs. So Go performs the best. Then it goes Scala, and Erlang is the lowest. But interesting thing that for some reason Erlang has this spike in the beginning. We don't know what exactly causes that, so probably a little bit more research into what's happening there will be quite interesting, because this spike is quite consistent independently on the size of the messages, of the number of processes, and across the repetitions of the same experiment. Right, so to sum up, just a little bit of takeaway message is that if we want to, if our system wants to minimize the message latency, then the best languages to go would be Erlang or Go. Then if we want to maximize the number of dormant processes, so if we expect in our system to have lots of processes that will just sit there but won't do much, that will be Scala with Akka. If you want to minimize the creation time, so we create processes, then we create them again, then in this case, Erlang is Go again. Throughput, so Go showed the best throughput performance, but again, there is no fault tolerance. It may not be a popular outcome for this particular conference, but still, you know, it's useful to know. And then if you're interested in how your favorite language performs, please do repeat our experiments. The code is open source, and please send us the results. We'll be really excited to see those. So the results of this work are available on a paper. If you're interested, give me a shout. I'll send you the paper, you can find it on my webpage. There are quite a lot of work. As you saw, this is just the beginning of doing more research there. So the first thing is we want to elaborate our benchmarks. As you saw, we gradually were increasing how complex the benchmarks are. So first they were just exchanging messages. Then we introduced pairs. So we want to introduce a little bit more complex benchmark there. Then we want to investigate fault tolerance. So first of all, not all the languages support fault tolerance, right? And in this case, you know, it's sort of Erlang has a huge advantage. But those that support it will be interesting to see what's going on there. And of course, explore more languages. It's also would be quite interesting. So the next work is investigating scalability of ROS. And this was work done by our student, Isaac Jordan. He's at Amazon at the moment, and with Gerard and Phil. So first of all, motivation. There is quite a lot of robots now. The number of robots grows. The complexity of those robots grows. And also there is this folklore that ROS is good, but it's not good for scalability, it's not good for fault tolerance. But the thing is that there is no actually evidence for that. So roboticists who work with ROS, they know that, but there is no proof. And this is the gap we decided to sort of minimize. And first of all, what is ROS? So who's familiar with ROS here? Right, great. So a little bit of introduction. So ROS is around from 2007, and it's about creation of complex robot behavior, and it supports that. And it's a collection of tools, libraries, conventions. And the rationale behind that is that no single individual, group, or institute can actually handle the increasing number and the speed with which robots are developed. ROS is quite widely used. So it's big in Europe, in the US, in Japan, in robotics communities. And it provides access to hardware, to drivers, to development tools, to external libraries. And the rationale behind that is that we can use as much or as little of ROS as we like. And it also encourages collaborative development. So it's very big in academic community, because what they do, they would introduce a new, for example, driver or a new tool, and they would commit it to ROS so other people can use that as well. A little bit of overview. In some case, so it also has a distributed system, and we create these ROS nodes. These are software, and those ROS nodes, they communicate with each other. So, for example, we have a camera, and what a ROS node will do, it will, collect data from that camera, and then this ROS node, you can subscribe to it. So it has published subscriber communication model. You can subscribe to that model and just, collect streams from that camera particular. So, and nodes communicate with each other. There is a ROS master node, and it controls communication. In which way? So if two ROS nodes want to communicate with each other, they need to be registered with ROS master node. Communication won't go through the ROS master. The nodes will communicate directly with each other. But if a node is not registered with ROS master, then there won't be any communication. And then we can have communication between different ROS robots. And in this case, we create master ROS node. And again, they are the same thing. As you see, this ROS master is a weak point. So if it fails, the whole robot fails. And the whole communication between robots fails. It's also very unstable. So if one robot fails, there is a chance that your whole fleet will fail. Another thing to point here is that it doesn't say that ROS is bad. It says that it just wasn't developed for scalability and for fault tolerance, right? It was developed to support development of robots. And does a really good job. So these are my robots. I have 9 of those, 6 of them at the moment at Glasgow University and 3 at Bournemouth University. And they're quite interesting. So what we got, there were the boxes of those small robots, and they're relatively cheap. So if you want one, they will cost you, with batteries, with chargers, with everything, with sensors, they will cost you around £120. And they're really fun to assemble, but only the first one. For the rest, if you want, do find some labor to do it for you, because then it's just, quite boring and mundane thing. So we assembled them, and for this particular robots, we put Raspberry Pis. We are planning to buy more robots, and on those we will put grease cards to see how those will work. But the experiments you will see here, they're all with Raspberry Pis. And if you put it there, then it's really like cheap. Your single robot will be about £150, and it's really fun to work with them. So this is the setting for our initial experiment. And what we wanted to do here, we wanted to analyze communication of ROS. And here you see that what we did, we took 2 Raspberry Pis, and those Raspberry Pis start communicating with each other. They have a wired connection, and they're connected to mains power. And the master node, we put it on a different Raspberry Pi. It's just for fault tolerance. If something goes wrong, ROS master is sort of isolated, just to reduce the risk of failure there. So, if you compare to this picture, we have robots, but then we run experiments on these just Pis. And the reason for that, if you want to analyze something with robots, start really simple. Because initially what we did this really fun experiment, and it was like robots, they were following each other, we developed it, But then we couldn't understand what's going on. And what we did, we started simplifying things. We reduced the number of robots. And we thought, no, it doesn't work again. We thought, okay, we won't do like following each other. They will just standing. They will just exchange some meaningful information. And again, we couldn't understand. So we're going back until we came to just 2 Raspberry Pis. And each Raspberry Pi would have 1 ROS node. And those ROS nodes would just exchange simple messages like hello world. So if you want to work with them, just start really simple. Otherwise, it's really difficult to understand what's going on there. So we run the first experiment just to see what's going on there. And it shows that until we go 1 megahertz of frequency, message frequency sending, the communication latency is flat. It should be like consistent, right? The time takes to send each message is the same. So we have time in milliseconds, and then we have a number of time it took to send every message. So we sent 1,000 messages, and here it shows the time it took to send every individual message. And until we went to 1 megahertz, the time was consistent, and then it's time, jumping up and down. And then we said, well, what causes that? There are lots of things here. One can be just rebooting. Maybe after running each experiment, we need to reboot. Maybe something happening on with queues, caching, and things like that. Then probably type of connection. So what if we change Ethernet with Wi-Fi? And the third one was CPU speed. So Raspberry Pis are quite small. So what will happen if we actually put more powerful processor there? So this one is Ethernet speed, and we have message latency in milliseconds, and then we change the frequency. And then we have different frequencies, and for each frequency we have Ethernet in red and Wi-Fi in blue. And as you can see, when we switch from Ethernet to Wi-Fi, the performance, goes down dramatically. So when you test your system with robots on Ethernet, and then you change your Wi-Fi, it doesn't matter how stable it is, it's still, you will get, this dramatic drop in performance. Need to put in mind. And another thing is that rebooting, it actually didn't have any impact, so that was good. Our student was particularly happy because he didn't need to restart the Raspberry Pis every time. He would just run the script and run all the experiments. And then we did CPU speed, and here we underclocked. So we decided not to overclock because we could just see all sorts of, side effects from there. So we went for underclocking. We had 100%, that's in blue. Then red was 75% of performance, and then finally yellow is 50% of performance. And here we have message latency again in milliseconds and on different frequencies. And small frequencies, the performance almost the same, but as we increase the frequency, we can see significant difference in slower hardware. So the faster CPU, the better, obviously. Then we thought, well, we were just sending hello world. What will happen if we start sending like real data from camera and from different sensors? So we decided to use the data that was collected by MIT for this PR2 robot. And there were two types of messages there. So the first one was sensor data, and the second one was video data. The significant difference, so the messages, first of all, have difference in frequency. So sensor data was 20 hertz and video data was 30 hertz. But the larger difference was in bandwidth. So in sensor, that was 85 kilobytes per second, and in video data it was 9.2 megabytes per second. So bandwidth is significantly different, but the size of the messages, that's where the main difference came. So sensor are relatively small messages, about 4 kilobytes, and videos are really large. They're about 30 kilobytes. Oh, 300 kilobytes, sorry. So we ran two experiments here. Rebooting does not have an impact, so we went for Wi-Fi and CPU speed, and to our delight, the result confirmed. So the result was just simply hello world. The conclusions we made from those experiments we can use actually in the real world, so that's good, that's hold. Regarding this, so this experiment, it just shows what we measured there and how it looks. So we're changing frequencies from 100 hertz to 600 hertz, and on low frequencies around 300 hertz, the latency was the same. But as we were increasing the latency, what we saw is that it takes the more messages we are sending, the longer it takes. So they're just accumulating, and they can't handle high frequencies there. And the last experiment we did was on vertical scalability. So vertical scalability is increasing the number of ROS nodes per robot or Raspberry Pi. So we ran to experiment, and the first one was with Raspberry Pis, and the second one was with robots. And what we did, we just increased the pairs. So now two Raspberry Pis, for example, talk to each other and they send messages. And this one was the simple one. It's just nodes, just two nodes, just talking to each other. They wouldn't talk to other things. And we were just growing the number of pairs. And here the difference is that, so Raspberry Pis in the picture here, they have a wired connection, but actually there was a Wi-Fi, just didn't put a picture, just for illustration. And they're connected to mains. Whereas robots, they have battery, so the energy is not as stable as on Raspberry Pi. So these are the differences. So the good thing was, so the features of these experiments was that we used representative data, again, not the hello world, but sensor and video data, Wi-Fi connection, and we used two different types of hosts. So Raspberry Pis, just bare Raspberry Pis, and Raspberry Pis on our KiKit robots. And the performance was around 4 nodes. We have like two pairs, 4 nodes in total, communicating with each other, and then the message exchange was sort of stable, but then as we increased the number of pairs, the performance was a little bit funny, and robots eventually failed and weren't able to deliver. But interesting thing that we found here was this communication scaling limit volumes. So we're not very good with introducing acronyms. So this is just, we called it what we saw there. And what it means is that there is this capacity that robots can exchange. And when they sort of when the limit comes, that's it, then your system starts behaving. So it becomes stress, and it won't perform at its best. And it depends on the number of nodes on the host. It depends on message frequency, and then the message size. An interesting thing is that if you measure that for your system, then you can predict how your system will behave. So, for example, you found the volume, and then you decided to change the number of nodes, for example, or change the size of messages, and then you will know how your system will perform. Whether, for example, when there will be 4 nodes, whether it perform well, or whether it will start failing. So that was really exciting outcome that we found there. And then the last experiment I would like to introduce you to is ROS. We compared ROS and Erlang performance, communication, and this was done again by our student. She's at the moment in Switzerland, and this one, it's Andrea Lutak who did this experiment. So what we did here, we have a robot and we have a camera, and the camera can turn, it can tilt, and we introduced this, and it does face recognition. So it just follows the face of a human. And we introduced 2 systems. One is using Erlang communication, and another one was ROS communication. We didn't reintroduce any drivers or anything, so all those were Python. So the only difference was different communication type. And so one of them was ROS, and it just used its own fault-tolerant system. And then with Erlang, we used Let It Crash, of course. And here are the really, really nice results that we've got. So we have frames, and so on the X, what you see is the number of each frame. And then at a certain point, we would kill certain percentage of processes. So in ROS, we killed 10% of all processes, and in Erlang, we killed 50% of the processes. And then, so you don't see it up and down, it should be like that, but all those lines, they should coincide with each other. That's the main thing. And what we saw in ROS, so we killed only 10% of the messages, and then system couldn't recover. So it was starting like trailing. So what we would see, the camera would start working a little bit slow, and this rectangle on the face, it would, start being slow again. And eventually it just crashed. But with Erlang, when we killed 50% of the processes, system was actually able to recover around 56 sort of frame. There was frame, we crashed it, 50% of the processes crashed, and we restored communication, and around 56 it was, performing again well. Another interesting thing, then when we were killing 10% and 25% of process, Erlang system even didn't notice that something went wrong. That was really exciting. So what Erlang did here is that not only reduced impact of failure, but it also mitigated it. Right, conferences. This is all about the research that we do, but there are also conferences. If you're interested, please come. So the first one is Erlang workshop, and it will be in September. And if you have a paper that you would like to submit, please do. The deadline is 15th of June. And we are looking not only academic papers, but we also look for experience report, and it's not only Erlang, it's functional programming in general, and it's Elixir, Beam, it's whatever language you like. And if you're just in the US, please come. Will be lovely to see you there. And there are also 2 other conferences. One of them happening in Gothenburg, Sweden, actually here, and it will be in June. So submission papers are closed, but it's Trends in Functional Programming. Please come. And the second one is IFL. It's also in Massachusetts, US. Paper submission also closed, but please come. It's another academic conference. And thank you very much for your attention and any questions. Thank you.